Hello everyone, welcome to 2024 Quarter 2 series of TAC webinars. Thank you for joining us today. I am Neha Sakalkar, currently in the role of team lead within the Arista Technical Services team. For those who are joining us for the first time or returning after a break, allow me to provide a brief overview of the TAC webinar initiative. The primary focus of TAC webinar sessions is to facilitate knowledge sharing based on TAC interactions with our customers. During these sessions, we dive into topics that are relevant and useful to most of our customers. Since its inception in 2022, we have covered various technical scenarios involving switch health checks, issues encountered in Layer 2, Layer 3, VXLAN, or EVPN environment. In today's session, we will explore two common issues observed with multicast traffic flow passing through the network. Devroy, can you move to the next slide, please? Our subject matter expert here, Devroy Peterson, will be our guide today, walking through the lab-based scenarios using Arista CLI. Additionally, we also have our seasoned engineers and technical leads to address any questions raised during the session. Please use the Q&A section of the webinar for any questions. Moving on, our registered attendees should also have received the link for topology diagrams in their inbox early last week. If you weren't on the registered list or haven't yet downloaded the copy, no worries. Our panelists will share a link to download the file in the webinar chat. We would recommend keeping a snapshot of it handy for quick reference. Can we move to the next slide, please? On this slide, you can see our schedule for upcoming webinars along with the registration link. Recording of all previous sessions, including slide deck, some sample configurations, and Q&A are available on our Arista community page linked on the slide deck. Now, before we move into technical troubleshooting, I would like to take a few minutes to introduce our new product offering called Arista TAC Custom Training. Based on your invaluable feedback and a growing interest in personalized training, we have launched a fully specialized paid offering led by our TAC experts. These training sessions are tailored to your platform, feature, and network design requirements. They include a comprehensive analysis of recent TAC cases associated with your account, reviewing common network issues, and providing key recommendations to prevent those issues in future. The good part is that these sessions are entirely presented in the form of troubleshooting session. This will ensure that your network operations team is ready to handle any challenges that may arise in your network. We have received excellent feedback so far on both the quality as well as the content of these sessions from many of our Cloud Titan as well as enterprise customers. If you're interested in scheduling a session or learning more about this offering, feel free to reach out to us at tac-custom-training@arista.com. Now, without further ado, I'll hand it over to Devroy to start with the technical content. Over to you, Devroy. Thanks.
All right, thank you, Neha. Hi, everyone. Thank you for joining me today for the troubleshooting session. Just a quick introduction. My name is Devroy. I've been in the TAC role for about 12 years. Now, when I started in TAC, one of my roles was a Layer 2 specialist. From a multicast perspective, that's essentially just IGP stooping, which sounds interesting, but IGP generally just works by default. It doesn't have a lot of customization. So honestly, for the longest time, I thought multicast was actually a boring technology. And it wasn't until I moved to the routing and data center space that I really got to see how interesting multicast could be. And being a TAC especially, I get to see some very cool and complicated deployments. And that leads into our session for today, though, which is going to be our first in our multicast troubleshooting series. Similar to the last webinar, I'll be walking you through some problem scenarios and questions that I've received often. I'll share the methodology I find successful for troubleshooting multicast cases, some useful CLI commands, and explanations of the multicast behavior as we go. This session is also going to be focused on troubleshooting from the last hop router perspective, since it's a common location for failures and where I like to start my troubleshooting. Now, before I start discussing our first scenario, I want to make sure everyone is familiar with these acronyms. I'm assuming everyone here has some familiarity with multicasts, so I'm not providing detailed explanations of the ins and outs of PIM, but I know in the networking world, we have a tendency to create acronyms for everything, so I just want to refresh people on these I'm going to be referencing often. RP is our rendezvous point. It's the root of our shared tree for multicast. Basically, the first hop router will register multicast streams to the RP, and the last hop router can request those streams from the RP. Next, we have the DR or PIM designated router. When you have two PIM routers on the same LAN segment, we don't want both of them trying to join or register a multicast stream for devices in that LAN segment because it'll result in duplicate packets. Instead, we elect one of the PIM routers to be the designated router. The designated router is going to be the one with the highest configured PIM DR priority. And if that's the same, the router with the highest IP address in that shared subnet is going to determine the DR. The other routers on the LAN segment would then be considered non-DRs. Now, if it's the only PIM router on the LAN, like how leaf 1 here is the only router on the source VLAN in the diagram, it'll become the DR by default. Now, depending on the direction of the flow, the DR could be a first hop router or could be a last hop router. For a first hop router, when a multicast source generates traffic and it's received by the PIM DR, it's going to register that traffic with a rendezvous point. For a last hop router, when a receiver sends an IGMP join, and it's received by the PIM DR, it's going to convert that to a PIM join and forward that to the rendezvous point. And for reference, this multicast path we see here from the first hop router to the rendezvous point, and then down to the last hop router, it's called the shared tree. Now, there will be some more acronyms we encounter throughout this scenario, but I'll make sure I speak to those as we hit them. So let's look at our first scenario. Here, the customer has a new network they deployed where they want to receive exchange traffic on leaf 1 and have it forwarded down to the receivers off of other leaves. Talking to the customer, they tell me they've set up a single test receiver that subscribes to some multicast groups, and they're using that to validate the design before they move production servers over. However, their server team says that some of the streams are working just fine, but some never reach the receiver at all. Now, before I start troubleshooting this with the customer, the first thing I always ask on any multicast case is that I need to know the source, the impacted group, an impacted receiver, and the rendezvous point. And that's always going to be key to figuring out what's wrong. If I can't isolate a specific flow that's broken, I'm going to have a very hard time trying to isolate the root cause. So here are my initial thoughts just based off what the customer said. I don't necessarily share this all up front, but it's more things I have in mind to keep an eye out for as I troubleshoot. There's a lot of things that can cause multicast to not reach your receiver. The first thing I think of is maybe there's a routing issue. If we don't have a route to the rendezvous point, there's no way the multicast join from the last hop router will ever reach the rendezvous point. But the customer said some traffic works, so in my mind, there'd have to be something kind of peculiar with the routing if it caused these symptoms. Next, maybe there's a configuration issue. The customer said this is a new topology, and new deployments often have misconfigs. It's very easy to typo configuration or forget to add it, especially when you're configuring it all by hand and not through some kind of automated process. Just thinking quickly off the top of my head about what configurations could cause multicast black holing. Maybe there's an ACL with a bad prefix. That can be very easy to miss. On the same train of thought, maybe there's PIN boundaries configured that match our groups incorrectly, or maybe some groups have been set up with a bad rendezvous point. Outside of that, maybe there's an issue with the sender. Now, honestly, that's not as likely in an exchange environment, but it's not unheard of to have a source that just doesn't send the streams we think it's sending. More commonly, I see receivers not joining the stream, or maybe the application incorrectly leaves the stream. And then from a traffic perspective, I've seen some streams not sent with the appropriate TTL, so it makes it partially through the network, and then the TTL expires and the traffic's lost that way. Now, these are pretty niche failures, but that's where I'd like to emphasize again that these are things I have in mind as I troubleshoot. It's important to me not to let it drive my troubleshooting. If I jump around trying to check every potential cause for black hole scenario on every switch, I'm going to lose track of what I'm doing and why I'm doing it. And I see this actually common in high impact scenarios where you have multiple people trying to drive the troubleshooting. Instead, and this is what I tell our new hires as part of our new hire troubleshooting trainings, we should leverage a focused step-by-step methodology that allows us to isolate and validate these in an orderly fashion. So here, what I want to do is start with the last hop router. Multicast leverages a pull mechanism to receive traffic. So if I want to verify the path the multicast traffic takes, I need to start on the receiver side. what I want to do on the last hop router is check our multicast states for IGMP and PIM. Now, if you're familiar with multicast, you will know if your last hop router has an SG or source group entry, we know it's receiving the traffic and the issue is likely between the last hop router and the receiver. Likewise, if we don't have that SG, we want to move our way towards the rendezvous point to validate where the multicast was last seen. And then theoretically, if you make it to the rendezvous point and the rendezvous point isn't aware of that source group, it's time to look at our first hop router registration to figure out what's failing there. But let's dive in with a CLI investigation. So as you probably see, the receiver is directly connected to leaf 2B. So that's where I want to start my troubleshooting. Now, this is just a habit of mine. I always like to check the route towards the receiver. Just because you have an ARP entry here doesn't mean the receiver is necessarily connected here. I've had a scenario before where I was told the device was connected to one location. We had an SVI and an ARP entry, but the route to the receiver was actually a /32 route to a different VTEP. Now, theoretically, there's no VXLAN here, but like I said, it's just a habit I have now to validate before I move forward. With a directly connected route, I move forward to check our ARP entry. And this confirms receivers should be connected off port channel 30. And you'll notice on the right, I try to keep my diagram updated as I go. This isn't just for the presentation, but whenever I'm on a troubleshooting call, I do the same thing. So I can reference it later to validate what I did, and I use it for my root cause analysis. So I validated ARP. I'm going to go check IGMP snooping now for the impacted group. One thing I like to do here is specify the local parameter in the command. MLAG does something called IGMP sync. If you have an MLAG port channel going down towards a host, the IGMP membership report is only set up one of those member interfaces. This command would tell you if the IGMP membership report was received on the local interface or if our peer received it and synced the information to us. So here I run the command, and since we have an entry here, we know it's a local entry, which makes sense because the customer hasn't deployed the MLAG port channel yet to the receiver. Now, since it appears IGMP is in order, I'm going to validate our configurations. On the layer 2 interface, our port channel, I want to look out for any port ACLs or unexpected IGMP configurations, but it looks fine. Moving to the SVI, I'm going to do the same thing, make sure there's no abnormal PIM configurations here. Here, we just have the IP address and PIM sparse mode, which is what we need for multicast routing. So now I feel comfortable moving to our mRoute state. So I check show IPM route for that impacted group. And I see this behavior here, or this output. We have that 0000*G entry for the group, which tells us that PIM is aware of the interested receiver, but the incoming interface is null, and I don't see any outgoing interface. So what I want to do is compare this to our working group just to understand if this is expected. And here the *G entry looks the same, so we can assume it's expected. We also see a source group entry here, but it also shows that null incoming interface, or IIF. Now, the primary reason you would see this on a last hop router is we're not the designated router. Again, when you have multiple PIM routers on the same LAN segment, we only want one of them to try to join the multicast stream, or we end up with duplicate packets. Now, generally, people don't modify the PIM DR priority, so you'll find the designated router is the router with the highest IP address in the LAN, which in this customer's case, they said should be leaf 2B. But we can validate who the DR is with the command show IP PIM interface. So we check this for VLAN 30, and we see our IP address is .3, but the DR is .2. The customer set a DR priority on the MLAG peer switch of 100, and the highest DR priority takes precedence over the higher IP address. So the peer switch is actually the designated router. Now, the other way you could check this is by checking the mRoute detail command. This one shows that we would theoretically have an outgoing interface for VLAN 30, but we're not the designated router. So this can be a very useful command to check if you're not seeing the proper OIF or outgoing interface you expect. But since we know leaf 2A is our DR, we're going to check the state here. I'm going to double check the route. Again, it's rarely the case it's wrong, but it takes me 2 seconds to validate. Checking ARP, I see port channel 2000. Now this receiver is an orphan port off of leaf 2B, so I'm guessing this is the MLAG peer link, but I'm going to check show MLAG just to validate that the peer link is port channel 2000. And here it is, so that looks good. So based off that, our snooping entry should also point to port channel 2000. This time I specify MLAG in the command, so I can confirm that leaf 2A received an IGMP sync from leaf 2B. So our IGMP state looks good. We're going to check our mRoute now, just like we did on leaf 2B. So starting at the top of this output here, we see the *G entry, and we believe the RP is at .99 address, which lines up with what the customer told us. The flag of W is normal here. It just says it's a wildcard entry. We have an incoming interface of 49/2, which lines up with our RPF path, or our reverse path forwarding route, which says it's a /32 BGP route via one of the spines. Now you have to receive the multicast on the RPF route or else it gets dropped. And then finally, we see the outgoing interface as being on 30. But I don't see an SG entry here. When a switch receives multicast traffic but doesn't have an associated SG entry, the multicast traffic is temporarily forwarded to the CPU to inform the PIM agent of the new source. PIM will then create the SG entry, which would reflect in that MRoute output. Now, since we don't see the SG entry, it tells me the switch is not receiving the multicast traffic. So I compare it to our working group, and here we do see the populated entry, but look at this, the IAF for the StarG is different. Now, this can be different based off of your routes. So I check our route towards the rendezvous point, and I see we have ECMP routes. So our PIM join is hashed to different next hops depending on the source of group we're trying to join. In this case, we happen to hash our PIM join to different next hops. Another way you can validate this is with the command show IP PIM upstream. This command tells you which PIN neighbor off of which interface you would send the PIM join to for a specific group. Now here, what I want to do is run it for our working and non-working groups so I can compare them. So I see that our impacted group has a PIM upstream PIM neighbor of .9 off of interface 49/2. Their working one is via neighbor .1 off of 49/1. Now, just to validate the topology, I'm going to check LLDP. Usually the topologies are right, but often they're outdated. So I like to recommend checking LLDP to make sure your next hop is what you expect. We specifically care about 49/2, which goes to spine 2. So let's move there and see what state it has there. I'm going to start with the MRoute here. And when we check this, we already see a problem. The rendezvous point is correct, but the incoming interface is null. Now we're not in LHR or FHR, so the DR doesn't matter here. What I'm going to do is check to make sure we have a valid route to the rendezvous point, and that looks correct. And I'm going to check LLDP again to make sure that goes where we expect. So it goes to the super spine. I wonder what spine 1 shows for our working group though. So I'm going to do the same thing and check our MRoute because it should have the proper state here. And here the StarG does show the correct incoming interface, which again, I'll confirm with LLDP to make sure it goes to the same super spine. And then once I do that, I want to check our PIM interface state, show IP PIM interface, before I jump to spine 2. Now, a quick note here, I do see some packets dropped. This indicates historically there may have been some issues on the switch, but since it's currently not in the path of our issue, I take note of it, but I'm going to move on and we'll investigate that later if needed. So going back to spine 2, I'm going to check our PIM interfaces here to see if there's anything abnormal with that 1/3 uplink. And what I notice is when I run this command, there's no entry for the interface, which means PIM is not enabled on the interface. Since the interface is up, I'm going to check our running configuration. And here I see there's no sparse mode. Now, a quicker way to identify this type of misconfig is through the command show IP PIM config sanity. And this here shows we have a route that goes via a non-PIM interface, which isn't allowed. And this is a useful command for finding other types of misconfigs too. But here I'm going to configure 1/3 for sparse mode, and then we'll want to check the MRoute again. Because with sparse mode enabled, we should be sending that join up to the RP and receiving traffic on that shared tree now. So now when I check our MRoute, I expect to see the proper incoming interface and SG state. So things should be working now with an outgoing interface of a 1/1 going down to leaf 2A. I'm going to move to leaf 2A and check the state there again. Now I'll expect to see the same StarG entry here, but we should have an SG entry now that reflects that we're receiving that multicast traffic. And it looks like it's good. We're receiving the traffic and routing into VLAN 30, which will go over to our peer switch, leaf 2B. Now I want to check 2B just to validate what the state looks like here. Similar to the working state, I expect to see the SG entry with an incoming interface of null. And that's fine if we do see that there, because we're not the DR. So let's pause here and do a quick recap of what we looked at here. So we first isolated a specific impacted flow, and we started from the last hop router and worked our way towards the rendezvous point. And then on each hop in the path, we validated our multicast state. More specifically, what we found was that the receiver sent an IGMP membership report that was received by our leaf 2B. We saw that synced that IGMP state to leaf 2A. Leaf 2A generated a PIM join to spine 2. We know that spine 2 received the PIM join, but it couldn't generate its own PIM join, as its RPF interface, the route towards the rendezvous point, was not PIM enabled. And since the RP was not aware of this receiver, that shared tree was never completed and the traffic couldn't flow to the receiver. And to recap the commands we looked at here, we checked our IGMP snooping table to validate which MLAG switch received the IGMP join. Here, we did find the leaf2b received the join. Theoretically, if we had no entry at all, it would mean we weren't receiving that IGMP join. We used the show IP PIM interface command to determine which PIM router was a designated router and to validate which PIM interfaces, which interfaces were PIM enabled. We checked show IP mroute to verify the proper incoming interface and outgoing interface. And we noted if we don't have an SG entry, the switch is not receiving the multicast traffic. And then we also used show IP PIM config sanity to highlight any relevant misconfigs we had. So let's move on to scenario 2. A few weeks pass and the customer calls in again. Things have been working in the network and they've been able to move most of their production servers over to the new network. However, they're seeing some issues again. At the beginning of the day, some of the servers aren't receiving multicast traffic, though by the end of the day, the issue seems to resolve. They've noticed it's not all groups impacted. The impacted group today might work fine tomorrow. And they found that they can have servers side by side in the same VLAN where one receives it, but one doesn't. Again, before I start troubleshooting, I get this fundamental information. I need the source, the group, our receivers, and the rendezvous point. So here's what runs through my head when the customer first describes the issue. The biggest thing to me is they mention a time of day, and that's actually really useful information. It tells me there's some event that's causing this behavior. Now, maybe that could be a scale issue where too many servers are sending too many IGMP joins at the same time and they're being dropped, or there's some other type of IGMP churn. Maybe there's another network event that coincides with state creation and causes issues. They also said that not all servers or groups are affected. We have a working and non-working server on the same last hop router for the same group. That points to a last hop router issue because we know it's receiving the multicast because it makes it to some of the receivers. Again, maybe there's an IGMP issue, maybe there's a layer 1 issue going down to the impacted servers, but I'll keep in mind as I troubleshoot. From a methodology perspective, it's going to be pretty similar to what we did before, but I'm going to focus more on the last hop router given those symptoms. I want to confirm our multicast states, compare our working and non-working flows and receivers, do some general health checks on the system, and if that looks fine, I'll move a little bit into the hardware programming. So let's start investigation for scenario 2. Now, I'm going to start with the last hop router, like I said, and specifically, I'm going to start with leaf2a, since we already confirmed it's a designated router for the server VLAN. I check the mroute, and I see the state I expect. Specifically, I'm validating we have that SG entry, which proves we receive the traffic. The incoming interface is going to be 49/2, and the outgoing interface shows VLAN 30. Now, once that traffic is routed into VLAN 30, the switch will forward that multicast traffic to any IGMP mrouter ports and to any of those IGMP snoop ports. Just as a quick explanation, an IGMP mrouter port is any port that faces a multicast router or electric querier. The idea is that multicast always has to flow towards multicast routers and queriers in case they know about multicast receivers or local devices I'm aware of. But here, leaf2a should have an IGMP snooped entry that shows port channel 20, our working server, and port channel 30, our impacted server. So I run the command here. I see port channel 20. I don't see our impacted interface, port channel 30, but do see our peer link. So that's interesting. Maybe we're not receiving the IGMP join from our impacted receiver. Maybe there's an interface issue. Interfaces are easy to troubleshoot, so I start layer 1. I check out port channel, and it shows our local interface is configured but down. Talking with the customer, it turns out the servers are technically set up with a second interface, but the server team hasn't finished deploying the NIC bonding yet, so they only have one interface up. That lines up with this output where we see peer Ethernet 1 is up. We did see the MLAG port channel was listed in IGMP snooping, so the traffic should still be forwarded towards leaf2b and then down to that receiver. So that looks like it should be okay. For the sake of checking for any errors, I'm going to check show logging. And here I see there's an IGMP version 2 query heard on VLAN 30 by a querier configured for version 3. This is a very common log message we see, and it's actually cosmetic in nature. IGMP v3 is backwards compatible with IGMP v2. It's fine to receive v2 queries from membership reports. This message is mostly informative in case you're expecting to run version 3 everywhere. For example, receivers ought to be sending source-specific joins. But at this point, Everything on leaf 2A looks fine. It should be forwarding the multicast to leaf 2B and down to the receiver. So I'm going to move our investigation to that switch. Again, I'm going to start with our M route. The M route looks correct. We have an SG entry, so we know it receives the multicast traffic from the designated router. So I'm going to check our IGMP snooping groups now. And what I expect to see is port channel 30 populated here. And it is. So everything so far says it should be working from a software state. But I keep in mind, we're looking at software states. We might want to go one level deeper to our multicast fib. Now, the underlying implementation of hardware programming is a bit outside of the scope of what matters here, but the multicast fib essentially takes information from those PIM agents and exports it down to our actual forwarding agents. So I'm going to check this show multicast fib IPv4 command for our group. I expect it to look sort of like our mroute output, which it does. I see the star G, the SG, and they both show null incoming interfaces. But just for the sake of comparison, I'm going to check it for our working group. And I see a difference here. One of these shows fast drops in the incoming VLAN. And I'm just going to pause here for a couple of minutes and talk about fast drops. When we look at show IPM route, what we're looking at is what the software thinks this route should be. For example, on leaf 2A, we saw the traffic should ingress 49/2 and be routed into VLAN 30. But what happens when we have a null incoming interface or receive that multicast traffic on an interface that doesn't match our incoming interface? Technically, that should fail RPF, our reverse path forwarding check. You see, when we talk about multicast flows, it's always going to be a tree, whether it's a source tree with a source as a root or the shared tree with the RP as a root. We use the term tree because these are specifically distribution trees, meaning they're unidirectional. If you think of a tree, the root of the tree is always going to be in the ground, and the tree goes up and out towards the leaves. It's the same with our PIM tree. The multicast feeds sources from the root of the tree and flows out towards the receivers. It's important that traffic always flows one direction from the root because it allows the multicast to be efficient, scalable, and more importantly, it prevents loops and duplicate packets. One of the main mechanisms we use to ensure the tree is loop-free is reverse path forwarding, or RPF. When multicast is received by a router, it ensures it's received on the interface facing towards the root by comparing that ingress interface to the interface we would use as a route towards the root. If it's not received on the correct interface, we need to drop it. And that's what a fast drop is. It's our route in hardware that says we're allowed to bridge the traffic, but we're not allowed to route it. So how do we actually program that fast drop? I mentioned before when we first receive a multicast stream, we send it to the CPU to create that SG route or SG entry. The traffic is going to be sent to the CPU until that SG entry is fully programmed in hardware. The idea is we want to continue to forward multicast packets in software while we program the multicast in hardware. If the traffic is coming in on an interface that's not our RPF, we still need to program that SG entry or SG route, but it's programmed so the multicast can't be routed. And again, once it's programmed in hardware, we'll stop sending that traffic to the CPU. So in our working group, we saw multicast fib had reflected the fast drop in VLAN 30, so the traffic is no longer sent to the CPU and it can't be routed. However, the broken group doesn't have that. So either the impacted flow isn't making it to the CPU, or more likely to me, the CPU is not able to program that fast drop correctly. Now, some of you might ask, if we can forward the traffic in software, why isn't the receiver getting this traffic? And the answer would be that behavior is actually platform dependent. On the 7280 switch, software forwarded multicast can only be forwarded down to multicast router ports and not to those IGMP snoop ports. Now, rather than just checking multicast fib, there are some other symptoms you would see while in this state. Commonly, you would see packets dropped in our PIM interface output, like we saw in scenario 1, which indicates that the PIM interface is receiving a lot of traffic it's supposed to process, but it can't keep up. So I'm going to check show IP PIM interface here and check for VLAN 30. And here I can see, yeah, there's a lot of packets dropped from VLAN 30. Now, another way you can see this is by checking our CPU counters. Now, which specific queue is used to buffer this traffic at the CPU can be platform dependent. Generally, when you check, it's going to show up here as our multicast misqueue. And again, I see a large amount of drops. Now, last, if I wanted to confirm it's our traffic at the CPU, I can run a quick packet capture to validate that. Here, I'm just going to do a TCP dump on our layer 3 interface, which is VLAN 30, and I'm going to filter it for our impacted group. And then I always recommend using the TCP dump C flag to limit the capture. Here, I limit it to 10 packets. And this validates the traffic's at the CPU, and multicast fib says there's no fast drop entry. So now I'm curious, what does actual hardware see? And that's where we can check the actual forwarding agent to double check what its state is. The command to check that is this show platform fap mroute command. It doesn't let you specify a group there, but this is what the default output will look like. Now, some of this requires context to interpret. The key things I look for is, does the entry exist? Does it have an incoming interface and the outgoing interface that I expect? And you'll notice the outgoing interface includes our IGP snooping memory interfaces. The forwarding agent receives information from multiple sources to build a single entry in hardware that reflects our forwarding state. What I want to do in this scenario is find the entry for our group. So what I will do, instead of spacing down through it, is I'm going to grep for our group. I also like to grep for one of the column headers so I can use it as a reference for reading the output. And interestingly here, I don't see an entry. We're not programming this in hardware for some reason. So let's compare this to a working group just to validate what this should look like, because the working group should have a proper state. And there's a bunch here. I see .4 in the middle here. So this confirms our impacted group is just not being programmed in hardware, but it doesn't explain why. Now, since the forwarding agent imports state from the multicast fib, I'm going to back up a step to the mfib again and see if there's any hints about what's failing. And specifically what I want to check here is our multicast fib summary to give me a summary of all the states. Oh, and here's a warning. The number of fast drops has reached the maximum of 512. This is problematic. By default, we only allow 1024 fast drops to be programmed in hardware. Any flows after that which require fast drop get sent to the CPU, and it fails to program any of those new fast drops. Now here I've modified that to be a 512 for the safe example, but you can see how at scale this can come into play easily. Now, the good news is we do log a message if this occurs, so catching the issue can sometimes be as easy as having proper logging or events or alerts set up in CVP. What I like to do if I'm on CLI though is I do show logging, and I'll do a grep for fast because I know the error message is going to be fast drop related. And yeah, I see a lot of these errors here. So how do we actually fix this? Well, we want to increase our fast drop maximum. Now to find out where that configuration is on the router, you can use the show run all command. By specifying all as a parameter, it will include our default configurations, which are normally hidden while viewing the configuration. Now, since this could be a lot of information, I recommend filtering the output to a section of the configuration. Here I know it's going to be a router multicast general configuration, so I do a section for that. And here I see router multicast IPv4, and then maximum fast drops is here. So to change this, I just need to increase that value to something greater than the number of flows I expect to see here. Commonly now, I see people just using 10,240. And we actually have an RFE file to make that the new default in future releases. A fair follow-up question is going to be, what's the impact from increasing this? Now, in practice, there's no impact. This doesn't reserve any space in hardware for the fast drop entries. It allows more access to the existing TCAM. Also, the fast drop entry occupies the same space our SG would use if we were the designated router. So it really doesn't matter if our max fast drop limit exceeds the actual number of SG entries I'll ever have, as long as the number of SG entries doesn't exceed the total capacity of the box. And at that point, honestly, fast drops aren't going to be your primary concern. You've got other issues going on. But now with that configuration in place, I want to see what multicast fib looks like. And here I see, great, the fast drops are in VLAN 30. It looks populated correctly. And I'm going to double check our hardware programming to make sure this is what I expect as well. And here, yep, I see the source group, incoming interface VLAN 30, outgoing, includes our snooping entry groups. So let's do a recap of all that. So first, we isolated a specific impacted flow, and we focused on the last hop router to validate where that flow was broken. We found that the non-DR switch had exceeded the number of fast drops it could program in hardware, so all the flows after the initial 512 couldn't be programmed in hardware, and were effectively black holed. Now, this would occur at the beginning of the day when the first 512 groups would program, but any after that would be impacted. As the day neared the end, as the receivers left those groups, eventually we'd have space in hardware to program those additional groups, and that's why it would work at the end of the day. And what we did to resolve this was we increased the maximum fast drop limit to 10,240. One thing I didn't mention here is that the initial information we received was incorrect from the customer, in that they thought we had the full M-like port channel connection down to the receiver. And that's kind of interesting because technically, if they actually had a full M-like port channel going down to the receiver, they wouldn't have noticed this behavior because Leaf 2A would have forwarded it down to that local receiver. And this might have bit them later because theoretically they lost redundancy, and any future orphan devices they would have had would have experienced this packet loss then. A quick recap of the commands we ran. Show IPM route we ran again. validating the incoming interface and outgoing interface. It was useful here to run on leaf 2B because it proved that our traffic was reaching leaf 2B because we had an SG entry. We checked our IGMP snooping groups to validate that the IGMP membership was received, or join was received. And here we saw it wasn't received on leaf 2A, which highlighted the fact that the layer 1 was down. Technically, that's fine. That's the point of redundancy to the online port channels row, right? Is we can go to our peer and then down. We checked our multicast fib state to validate it lined up with our mroute software state. And then we also dived into our multicast fib summary and show logging to identify warnings and errors related to those fast drop entries. And finally, for references, what I find is fast drops can be the hardest thing to wrap your head around, I think, for the common multicast issues. So we have two good articles our engineers wrote for this, multicast fast drops in general, and then one from fast drops in DR and non-DR environments. Because as you can see, it's expected to have fast drops in DR and non-DR topologies just because they're going to share IGMP states. We have a really good article for how to troubleshoot multicast that I always point customers to. And then finally, if you enjoy some of the under the hood stuff, as far as like what is fib and FAP mroute, we have a good multicast architecture as part of the configuration guide. That's really good. I personally like the hardware kind of stuff. And if you find that interesting, this is a good place to get started. But that's all I have here. I appreciate your guys' time.
Thank you, Devroy. Can you move on to the next slides? Thank you, Devroy, for sharing insightful tips on troubleshooting multicast packet loss. That was really a great session. We hope that it was beneficial to all of our attendees as well. Recording of today's session will be shared on our Arista community page shortly. Other than the few reference links that Devroy shared on the previous slide deck, our community page also includes a wide variety of articles on other technologies written by our in-house experts. We would strongly recommend you to leverage our knowledge base for that. Moving on, our next webinar session is scheduled next month on May 29th at 11 a.m. US Eastern Time. We are also including a link to a feedback form for today's session in the chat window. Please take a moment to share your feedback as it greatly assists us in selecting topics for future webinars. Now I'm going to keep the session open for a few minutes in case if you have any questions. Our panelists will be available to answer them live via Q&A. All right. Thank you, everyone. In case there are no other questions, I'm going to wrap up the session now. Thank you again for joining us today. We hope to see you back on our next webinar. Have a good day. Take care.